Hello students. So we have been discussing chapter 11 alcohol, phenol and ether. Okay. In last lecture we discussed about physical properties of alcohol and phenol. Today we are going to start new topic, that is chemical properties. So chemical properties of alcohol and phenol. Okay, now let me tell you one thing. Alcohol can act as nucleophile as well as electrophile. Alcohol can act as nucleophile as well as electrophile. Let us understand this. So in first case, alcohol can act as nucleophile. Okay. So in which case alcohol can act as nucleophile? For example, we have got alcohol. So this is alcohol, ROH. This is alcohol. Now we have got carbocation. So this is carbocation. Now in this case, this lone pair of electron of alcohol can attack on carbon which is having positive charge. So because of this, the product will be like this. And because of this bond of H is broken. So here this bond is broken. So it will look like this. Here O minus and H plus is there, and here carbon is there. Okay, it will look like this. So this H plus will be released. So because of this breakage of bond between O and H, H plus is released. So here in this case, alcohol is acting as nucleophile. Alcohol can act as nucleophile. Now whenever alcohol is acting as a nucleophile, the bond between oxygen and hydrogen is broken. Remember this. Now in second case, alcohol can act as electrophile. Alcohol can act as electrophile. Okay. Now, whenever alcohol can act as electrophile, alcohol should be protonated, which means proton should be added in alcohol. So suppose this is alcohol. Now proton is added, so it will look like this, ROH2. Okay. So this is protonated alcohol. Now, whenever there is reaction of alcohol as an electrophile, alcohol should be in protonated form. It should be in protonated form, which means it should have extra proton. Okay. Now, in this case, suppose this is Br minus or any halogen, right? This is protonated alcohol. Now this protonated alcohol will be released and this bond is broken. Bond between alkyl and oxygen is broken. So and Br minus will attack on alkyl group. So it will form like this, Br plus H2O. So the bond between carbon or alkyl group and oxygen is broken, and this negative group will attack on alkyl group and it will form bond with alkyl group, and this OS2 or H2O is released. So whenever protonated alcohol is acting as electrophile, the bond between carbon and oxygen is broken. So for the chemical properties, there are two types of properties, in which first property is in which bond between oxygen and hydrogen is broken. Second property is bond between carbon and oxygen is broken. Again, I am repeating this thing. Chemical properties of alcohol are of two types. First property, that is based on breakage of bond between oxygen and hydrogen. So first property is based on breaking of oxygen and hydrogen bond, and second property is based on breaking of carbon and oxygen bond. So there are two types of properties. We'll discuss first type of property today. We'll discuss properties based on breaking of oxygen and hydrogen bond. Okay. So today we are going to discuss properties based on OH bond, breaking of OH bond. Okay. Okay. So first, reactions involve breaking of OH bond. So today we are going to discuss the reactions in which OH bond is broken. Like this. This is alcohol. Okay. This bond is going to be broken in chemical reactions that we are going to discuss today. Okay. So first chemical reaction based on breaking of hydrogen OH bond is acidity. So topic is acidity of alcohol. Okay. Now the question is, why alcohol is acidic in nature? What compound or which compound should be acidic? So those compounds which can donate protons easily are acidic, or we can say that those compounds which has got capacity to donate protons, they can act as acid. So here we are talking about acidity of alcohol, which means alcohol should have property to donate proton, or we can say that alcohol is donating proton. So when alcohol is donating proton, it can act as an acid. Now, which are the chemical reactions in which alcohol can donate protons? So chemical reactions are reaction with metals. Reaction with metals. So whenever there is reaction between alcohol and metal, especially or specifically active metals like sodium, potassium or aluminum, alcohol act as an acid. Let's understand this by one example. So we have got alcohol ROH. Okay. We have taken 2 moles of alcohol. It reacts with 2 moles of sodium. Okay. Now we are talking about breaking of OH bond. So this bond is broken. Now, whenever there is breaking of this bond, hydrogen is removed, or we can say that proton is getting released. So here this bond is broken, so hydrogen is released. So 2 moles of alcohol is there, so it will form H2. 1 hydrogen and 1 hydrogen, H2 is released. Now what is left? So here RO minus is left, that is known as alkoxide. Okay, this is alkoxide, and 2 moles of alkoxide is there. Here metal is there, and metal, as we know, it is having positive charge, so it will combine with alkoxide. So it will form sodium alkoxide. So this is sodium alkoxide. Sodium alkoxide. Okay. So we can say that whenever alcohol reacts with any active metal like sodium, bond between oxygen and hydrogen is broken, and hydrogen is released. Now what is left? Alkoxide is left. Alkoxide can react with metal and it will form metal alkoxide. So this is sodium alkoxide. Let's understand this by one example. We have got 2 moles of phenol. So this is phenol. It reacts with sodium. So as we know, the bond between hydrogen and oxygen is broken. So this bond is broken. And we have got 2 moles of phenol, so H2 is released. So hydrogen is of 2 moles, so it will be released in the form of H2. Now what is left? So we have got phenoxide. So this is phenoxide. Phenoxide can react with sodium because sodium has got positive charge, so it will form sodium phenoxide. So this is sodium phenoxide. Sodium phenoxide. So sodium phenoxide is formed. Okay. So phenol reacts with sodium, bond between oxygen and hydrogen is broken, and it will form H2. So hydrogen is formed, and what is left? Phenoxide is left. Oxygen on the benzene ring, oxygen minus charge on the benzene ring is known as phenoxide. So phenoxide reacts with sodium and it will form sodium phenoxide. Okay. So this reaction shows that whenever alcohol reacts with any metal, it will form alkoxide or phenoxide and it will release hydrogen. So in every case, hydrogen is released. Now let us understand this by one more example. So we have got tertiary alcohol, CS3, CS3, CS3OH. So this is tertiary alcohol. As you can see that OH containing carbon is attached with 3 carbons, that is known as tertiary, right? So this is tertiary alcohol. We have taken 6 moles. It reacts with 2 moles of aluminium. Now as we know, the bond between oxygen and hydrogen is broken. This bond is broken. So it will form, see, 6 hydrogens are released. So it will be released in the form of 3H2. Okay. So first product is, this bond is broken. So hydrogens are released. 6 hydrogens are released. So 6 hydrogen can form 3 moles of H2. Now what is left? So we have got alkoxide, tertiary alkoxide. This is tertiary butoxide. We can say that tertiary butoxide. 6 moles of tertiary butoxide and we have got 2 moles of aluminium. Because it is having -1 charge and aluminium has got +3 charge, so it will form like this. So here, this butoxide will form bond like this. Okay. So 3 moles of 2, 3 are 6 moles of butoxide is there. It will combine with 2 moles of aluminum. So this is final product. This is known as aluminium tertiary butoxide. Aluminium tertiary butoxide. So why have we have written 2 moles? Because 2 moles of aluminium can react with 6 moles of butoxide and it will form 2, 3 are 6 moles of butoxide and 2 moles of aluminum. So aluminum reacts with butoxide and it will form aluminium tertiary butoxide. Okay. Now, all these reactions suggest that alcohol reacts with metal and it will form alkoxide, or alcohol or phenol can react with metal and it will form phenoxide. So these all reactions suggest that alcohol is releasing H plus because bond between O and H is broken, so H plus is released. So whenever any compound donates H plus or releases H plus, it is acting as an acid. So we can say that alcohol are acting as an acid. So these all reactions suggest that alcohol are acidic in nature. Let's see one more example. So we have got phenol. Okay, so this is phenol. Phenol reacts with NaOH, sodium hydroxide, and as we know, this bond is broken. So H plus from phenol, OH minus from NaOH, it will form H2O. So H2O is formed. Now what is left? Phenoxide is left and sodium is left. So it will form sodium phenoxide. So sodium phenoxide is formed. So phenol reacts with base and it will form sodium phenoxide. This reaction also suggests that because alcohol or phenol can react with base, NaOH is a strong base. So phenol must be acidic in nature, and because of this, it can react with base. Because phenol can react with base, so it suggests that phenol is an acid. phenol is acidic in nature. Okay, so these all reactions suggest that alcohol and phenol can act as an acid, or they are acidic in nature. Okay, so we have discussed till now alcohol is acidic in nature. Specifically, we can say that alcohol is a Bronsted acid. Now, what is Bronsted acid? That we have studied in standard 11. Bronsted acid is an acid which can donate H plus, right? Those acids or those compounds which can donate H plus are known as Bronsted acid. So, alcohol is a Bronsted acid. Let's understand this by one example. So, we have got base. This is base. Alcohol, we are writing like this. This is alcohol. Okay. Now, as we know, this H plus is donated by this alcohol. This is alcohol, and bond between O and H is broken. So this H plus of alcohol is donated by alcohol to base, and it will form product like this. So this is conjugated acid. Conjugated acid. Now what is left? So this bond is broken. So RO minus is left. So alkoxide is left, and it can act as conjugated base. So this reaction suggests that alcohol is donating H plus to base, and whenever in any reaction any compound donates H plus, this compound is Bronsted acid. So in this case, alcohol is donating H plus to base, and it is forming conjugated acid, conjugated base. So since alcohol can donate H plus, we can say that alcohol is Bronsted acid. So alcohol is Bronsted acid. Now, primary, secondary and tertiary alcohol, if we were asked to define the order of acidity in case of primary, secondary and tertiary alcohol, which order would be there? So we can write, so this is primary alcohol, RCH2OH, CHOH, this is secondary alcohol, RCOH, this is tertiary alcohol. This is primary alcohol, this is secondary alcohol, and this is tertiary alcohol. Now we have been asked to arrange this primary, secondary, and tertiary alcohol in acidic order, increasing or decreasing acidic order. So which is stronger acid? Primary, secondary or tertiary, and why? Now, the acidity of this alcohol, let's say this is alcohol, the acidity of this alcohol is because of its polar nature. Oxygen is having negative charge, so it will have minus delta. Because it is having higher electronegativity, hydrogen will have positive charge. So alcohol has got polar nature, it is polar in nature, and because of this polar nature, it is a Bronsted acid, or it is an acid, we can say that. Now, as we have know, we already know that because of polar nature of alcohol, it is acidic in nature. Now, one alkyl group is there, two alkyl groups are there, and three alkyl groups are there. Okay. Now, alkyl group is electron donating group, so it can donate electron. Alkyl group can donate electrons. Now, because of this electron donating nature of alkyl group, the polarity of OH bond decreases. So this polarity decreases, and as polarity decreases, the acidic nature decreases because it has got less tendency to donate H plus. So the acidic strength will look like this. Again, acidity of alcohol is because of polar nature of this OH group, right? As we know, polar nature means this is minus charge, this is plus charge, and because of minus plus charge, it is polar in nature. Now, alkyl group has tendency to donate electrons, so it can donate electrons. Because of donating nature of this alkyl group, oxygen will have more electron density. So here more electron density is there. So more alkyl group, more electron density is there, and because of more electron density, it will have less polarity, and because of less polarity, it can have less acidity. Okay, so more polarity, more acidity, less polarity, less acidity, and polarity is affected by alkyl group, more alkyl group. So we are discussing acidity of alcohol and water. So we are saying that water is more acidic than alcohol. Please remember this statement for short question answer. If we are asked to compare acidity of water and alcohol, we can say that water is more acidic than alcohol. Let us understand this by one example. So we have got a base. Alkoxide is a base. This is water. It is acting as an acid, right? So water is donating H plus to base. So this alkoxide is gaining H plus and it is forming alcohol, that is conjugate acid. Now since H plus is donated from this water, it will form OH minus, which is conjugate base. So here water has got more tendency to donate H plus. Water has got more tendency to donate H plus. Since it can donate H plus easily, it is more acidic in nature. So water is more acidic in nature compared to alcohol. And here also, alkoxide is accepting or gaining H plus. So since alkoxide can gain H plus or can accept H plus easily, it is a stronger base. So there is comparison between alcohol and water. So alcohol is less acidic, water is more acidic. If there is comparison between alkoxide and sodium hydroxide with respect to base, if there is comparison between this alkoxide and sodium hydroxide, we can say that alkoxide is a stronger base. So compared to alcohol and water, water is a stronger acid, whereas alkoxide and sodium hydroxide, when we compare basic nature of alkoxide and sodium hydroxide, we can say that alkoxide is a stronger base. Okay. Now, alcohol has got dual property. Alcohol can donate H plus and it can act as Bronsted acid. And since alcohol has also got, see, this is structure of alcohol, right? Alcohol has got lone pair of electrons, so it can accept H plus and it can act as Bronsted base, right? So alcohol can donate H plus and it can act as an acid, whereas alcohol can also gain or accept H plus because it has got lone pair of electron, so it can accept H plus and it can act as Bronsted base. So we can say that alcohol act as an Bronsted acid or alcohol act as an Bronsted base. Okay.
The bond between the C and the O breaks in the alcohol as the products form. Essentially, we can separate the reactions of alcohols in two major classes. Reactions involving cleavage of the oxygen-hydrogen bond, which occur for both alcohols and phenols, and reactions involving cleavage of the carbon-oxygen bond. Only alcohols undergo reactions that break the carbon-oxygen bond. We'll start with the reactions that involve the cleavage of the oxygen-hydrogen bond in alcohols and phenols. Alcohols and phenols react with active metals, such as sodium, potassium, and aluminium to form alkoxides or phenoxides and hydrogen. The general formula of the reaction is shown here. Notice that the OH bond breaks as the metal alkoxide forms. Try to solve this problem on your own before checking the answer. Write the chemical equation for the reaction of propan-1-ol with potassium. A reaction between an alcohol and potassium metal will form a potassium alkoxide. In this case, potassium propoxide forms as shown here. Phenols react with aqueous sodium hydroxide to form sodium phenoxides. Water is a byproduct of the reaction. Note that alcohols do not react with aqueous sodium hydroxide because they do not have enough acidity. The reactions we just studied illustrate that alcohols and phenols are acidic compounds. Phenols are comparatively more acidic than alcohols. They are Bronsted acids or proton donors. As the equation here shows, they can donate a proton to a stronger base. Alcohols can donate protons because the oxygen-hydrogen bond is polar. Since oxygen is more electronegative, it has a partial negative charge. The hydrogen has a partial positive charge. Let us now understand why primary alcohols are more acidic than secondary alcohols, which in turn are more acidic than tertiary alcohols. The presence of alkyl groups in alcohols increase the electron density around oxygen by the inductive effect. As alkyl groups donate electron density to the oxygen-hydrogen bond becomes less polar. It then becomes difficult to remove an H+ ion from the alcohol. The inductive effect explains the relative acidities of alcohols. Methyl and primary alcohols, which have the lowest degree of the inductive effect, are slightly more acidic than secondary alcohols. Secondary alcohols are slightly more acidic than tertiary alcohols, which have a strong inductive effect. Alcohols are weaker acids than water. We know this because alkoxide ions react with water to form the alcohol, the conjugate acid, and a hydroxide ion. Since this reaction favors the products, it means that water is a better proton donor than the alcohol. Versatile alcohols can also act as Bronsted bases or proton acceptors. The reaction here shows an alcohol accepting a hydrogen ion or proton from HCl. Phenols are also acidic in nature. Note that the benzene ring acts as an electron withdrawing group. The resonance structures of phenol, shown here, illustrate that the oxygen atom in phenol has a partial positive character. Phenols are Bronsted acids or proton donors. In fact, phenols are stronger acids than water or alcohols. The presence of the aromatic ring leaves less electron density on oxygen. So, the oxygen-hydrogen bond is more polar. This makes the loss of a hydrogen ion more favorable. The phenoxide ion forms when phenol ionizes by losing a hydrogen ion. The resonance structure of the phenoxide ion are shown here. Notice that the negative charge of the ion is delocalized which stabilizes the ion. On the other hand, in the alkoxide ion, the negative charge is localized on oxygen, which makes it less stable. The charge delocalization favors the ionization of phenol. Note that, in phenol, the charge separation in the resonating structures makes it less stable than the phenoxide ion. Hence, phenols lose a hydrogen ion more readily than alcohols. In other words, phenol is a stronger acid than alcohols. We can also discuss acid strength by comparing acid dissociation constants, or Ka. Strong acids have large acid dissociation constants. pKa values are also used to compare acid strengths. The pKa of any acid dissociation constant is defined as the negative log of the Ka value. Since pKa is a logarithmic function, as the Ka increases, as acid strength increases, the pKa value decreases. Therefore, a higher pKa value corresponds to a weaker acid. Try to reason this problem out on your own. Which one would you expect to have the higher pKa value? Ethanol or phenol? How should their pKa values compare to water? You have learned that phenols are stronger acids than alcohols and water. You also know that water is a stronger acid than ethanol. Finally, you learned that stronger acids have lower pKa values than weaker acids. So, phenol should have a lower pKa than water and ethanol. Water should have a lower pKa than ethanol. You can confirm your reasoning by comparing the actual pKa values. As expected, phenol has the lowest pKa and ethanol the highest. Substitutions on the benzene ring of phenol can alter phenol acidity. The presence of electron withdrawing groups, such as the nitro group, make phenols more acidic. This is especially true when the electron withdrawing groups are in either the ortho or para positions. In these positions, nitro groups allow for resonance structures that stabilizes the phenoxide ion by allowing more delocalization of negative charge. Conversely, the presence of electron-releasing groups, such as alkyl groups on the benzene ring, result in weaker acids for substituted phenols. For example, compare the pKa values of phenol and cresol. Phenol has a lower pKa value than cresol, reflecting that phenol is the stronger acid of the two. Remember that pKa values use a logarithmic scale. It's time to turn our attention back to reactions of alcohols and phenols. One important class of reactions is called esterification. Both alcohols and phenols react with carboxylic acids to form esters and water. This reaction is slow and reversible. Sulfuric acid is used as the catalyst in this reaction. Alcohols and phenols can also react with acid chlorides to form esters. These reactions are carried out in the presence of a base, such as pyridine. The base neutralizes the hydrochloric acid as it forms, which causes the equilibrium to shift right. Additionally, Alcohols and phenols can react with carboxylic acid anhydrides to form an ester as well as a carboxylic acid. These reactions are slow and require heating. Try to work out this problem on your own before continuing. Write the structure of the primary product formed when benzoic acid and N-propanol are combined in the presence of sulfuric acid. Start by drawing out the structures of the reactants. You should recognize this as an esterification reaction. Propyl benzoate is the main product of the reaction. One application of esterification is the synthesis of aspirin. Acetylation is the introduction of an acetyl group into alcohols and phenols. When salicylic